we will now look at some examples of surface integrals that involve flux. So this first example asks us to find the flux of the vector field F equal to x, y, and 0 through the surfaces of the tetrahedron formed by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Well, I first want to plot this tetrahedron. So I'm going to look at x plus y plus z equals 1. And I'm going to plot it using the intercepts. If I let x and y be 0, then z is 1. If I let x and z equal 0, then y is 1. And if I let y and z be 0, then x is 1. And that helps me plot the plane x plus y plus z equals 1. And so now that is one face of my tetrahedron. And then I can plot the other faces by thinking about x equals 0 and thinking about y equals 0 and, of course, z equals 0. So this tetrahedron has 4 faces. And what we're going to do is we're going to find the flux of the vector field through each of the 4 faces. So we're going to start with the plane x plus y plus z equals 1, and that's going to be our first face. So for face 1, that's going to be z equals 1 minus x minus y. Now the normal vector for that plane, you can read it off from the equation of the plane. You can see it's 1, 1, 1. But you can also see that by taking the derivative of z with respect to x, which is negative 1, and then multiplying that by negative 1, okay, or doing negative the derivative of z with respect to y, okay, which is negative 1, or 1, and then finally the third component is 1. Okay, so we have our normal vector n, and in this case then f dot n is just going to be the function x plus y. So f dot n, because z is a function of x and y, f dot n is going to need to be a function of just x and y so I can do my double integral. Had I gotten a z, I would have substituted in z equals 1 minus x minus y into that equation. Well, if I want to do my flux integral, so I want to compute flux, so I'm going to do a double integral over s of f dot ds. And that's going to be, as we defined before, it's going to be the double integral over my region. Let's call this region here R. So it's going to be a double integral over R of f dot n, which is f dot capital N dx dy. Okay, so now I need to describe the region in the xy plane. So I'm going to draw what this looks like in the xy plane. So here I have the line y equals 1 minus x, which is of course also that line there. So I'm going to do the double integral, okay, from 0 to 1 minus x. So I'm going to integrate dy first. I'm going to go from 0 to 1 minus x, and then from 0 to 1. I'm going to integrate f dot n, which is x plus y, and I'm going to integrate dy dx. Well, that's going to give me the integral from 0 to 1 of integrating dy. I'm going to get xy plus 1/2 y squared. And all of that's going to be evaluated between 0 and 1 minus x. And I've got to integrate that dx. Well, that is the integral from 0 to 1 of x times 1 minus x plus 1/2 times 1 minus x squared. If I expand this and do some manipulation, I can actually simplify this to the integral of minus 1/2 x squared plus 1/2 dx. And that's a pretty simple integral at this point. Okay, so this is going to be minus 1/6 x cubed plus 1/2 x evaluated between 0 and 1. And minus 1/6 plus 1/2 gives me 1/3. Okay, and so that is the flux through that first surface. We'll call that surface 1. Okay, now I'm going to start labeling the other surfaces so that we can look at the flux through those. So I'm going to do I'm going to look at when x equals 0, I'm going to call that 2. When y equals 0, I'm going to call that surface 3. And then when z equals 0, I'm going to call that surface 4. And now I want to look at the flux through those surfaces. Okay, so I'm going to start with x equals 0. Okay, that's surface 2. And I'm going to notice that finding the unit normal vector for this surface is super easy, okay? Because it's just the vector pointing to the left. Okay, so when I look at flux through that second surface, okay, my normal vector is going to equal -1, 0, 0, because it's going to be that vector pointing to the left. Well, then I can look at f dot n. F dot n in this case, okay, so that's x, y, 0 dotted with, okay, let's remind ourselves, I'm just going to put this here for assistance, that f is x, y, 0. Okay, so f dot n is actually going to equal -x. But it's -x on the surface, and that surface is the surface x equals 0. So in fact, f dot n, which is -x, equals 0 on that surface. So therefore the flux is going to equal 0. So if I do the surface integral of f dot n ds, the flux through that surface is actually going to be 0. Well, let's look at another surface. Let's look at the surface where y equals 0. And if we look at the surface where y equals 0, then we have, this was our normal vector for the second surface. Our normal vector for the third surface is kind of pointing into the page. Okay, And that's going to be the normal vector negative or 0, -1, 0. Well, then in that case, f dot n is -y, but we're on the surface y equals 0, so we're going to get 0. And so the flux through that surface of f dot n ds is going to be 0. Okay, so if we go through the plane y equals 0, we get a flux of 0. Okay, so these normal vectors I should have labeled. So this is this n2, this is n3. Okay, our last surface, okay, 4, is going to have a normal vector that's pointing down, n4. It's pointing down because we're looking at the flux out of the tetrahedron. So we're thinking about how fluid is flowing out of the tetrahedron. So in each one of these cases, I have it, the fluid, I'm measuring the amount of fluid that's flowing out of that object. Okay, so that's why you see all the negatives in these normal vectors. So let's look at that surface. So this surface is going to be the surface where z equals 0. And if I do f dot n4, where in this case, my normal vector is 0, 0, -1. Okay, it's pointing down. That's the unit normal vector. Then I'm going to get 0 just for the dot product. Okay, and so that's going to tell me that the flux through the fourth surface of that tetrahedron is in fact 0. So it turned out that the only non-zero flux was through the first face, the face of the plane x plus y plus z equals 1. So in this case, we have that total flux through all 4 surfaces was just 1/3. And so the only flux that's being measured is actually through that first surface where x plus y plus z is equal to 1. Okay, so let's look at another example. And in this example, we want to find a flux of the vector field. In this case, it's going to be x, y, z out of the region T that is bounded by a paraboloid. The paraboloid is going to be 1 minus x squared minus y squared. And the plane z equals 0. So I have the paraboloid that's making one surface. Okay, and the plane z equals 0 is making another surface. And I'm going to try to find the flux through both of those surfaces. Now, in many examples, they're just going to ask you to find the flux through one surface, but in a future video, we're going to be interested in finding the total flux through all of these surfaces. So that's why I'm going to do these examples where I find the flux through the first surface and then through the second surface. Okay, so let's find the flux through surface 1. Surface 1 is z equals 1 minus x squared minus y squared. And so the normal vector is going to be minus the derivative of z with respect to x. So that's minus negative 2x or 2x. And then minus the derivative of z with respect to y. So that's minus a negative 2y or 2y. And then 1. So that's my normal vector. And then I'm going to have f dot n that I'm going to need to compute. Okay, and I'll think about it as being n1. So f dot n1 in this case, so I'm going to dot xyz with 2x, 2y, and 1. And I'm going to get 2x squared plus 2y plus z. So here, f dot n is a function of x, y, and z. I'm going to need it to be a function of two variables on that surface. So to restrict myself to the surface, here I'm going to replace z with the equation 1 minus x squared minus y squared. So I stay on that surface. So in fact, f dot n is going to be x squared plus y squared plus 1. So if I want to find the flux through that surface, I'm going to do the double integral of s of f dot ds. Okay, and that's going to be the double integral of f dot n in this case. So this is ds1 for that first surface, so n1. So it'll be dx dy. And then I want to integrate over the circle x squared plus y squared is less than or equal to 1. So this is a double integral of x squared plus y squared plus 1 dx dy, okay, over the circle x squared plus y squared less than or equal to 1. X and y are going to be restricted to that circle, or the interior of the circle x squared plus y squared less than or equal to 1, okay, because this is the intersection of z equals 1 minus x squared minus y squared and z equals 0. Well, this is clearly a circular region. And so I want to do this actually in polar coordinates. So now that I've set the whole thing up in rectangular coordinates, I'm going to do the integral by changing to polar coordinates. So it's the integral from 0 to 2 pi, and then the integral from 0 to 1 with the radius. And then x squared plus y squared is r squared plus 1 r dr d theta. Well, the theta integral can be done separately. And then I'm going to do the r integral as the integral of r cubed plus r dr. The theta integral becomes 2 pi. And then the integral of r cubed from 0 to 1 is 1/4. And the integral of r from 0 to 1 is going to be 1/2. So in fact, I get that the flux through that surface is 3 pi over 2. So that is the flux through surface 1. But now I'd like to also find the flux through surface 2. So looking at surface 2, okay, so I'm going to have a normal vector here that's pointing down, okay, or my other normal vector, this was n1, this will be n2, but I can actually describe what the normal vector is as the unit normal vector. That's pointing down, so my unit normal vector in this case, when this is the surface, z equals 0, my unit normal vector is going to be n2, which is 0, 0, negative 1, just like in the previous example. And then when I compute f dot n2, I'm going to in fact get, well, what was my vector field f? It was x, y, z. When I dot that with 0, 0, negative 1, I'm going to get negative z. But the surface that I'm finding the flux through is z equals 0. Okay, so this is equal to 0 on the surface. Well, that tells me that then the double integral of f dot n2 ds. Okay, that flux is also going to be 0. So there's a flux through the surface of the paraboloid that's not 0. It's 3 pi over 2. But there's also a flux through the bottom of the surface that turns out to be 0. So here we had that the total flux through both surfaces is 3 pi over 2.